So thank you again, Fabio. So I'll start introducing you and then you can kick off the talk. Okay, so Fabio Roli is a full professor of computer engineering at the University of Genova, Italy. He is founding director of the Pattern Recognition and Applications Laboratory at the University of Cagliari, south of Italy. He is partner of the company PRALab that he co-founded, and he has been doing research on the design of pattern recognition and machine learning systems for 30 years. He has been appointed fellow at the IEEE and fellow of the International Association for Pattern Recognition. He was a recipient of the Pierre Divigier Award for his contribution to statistical pattern recognition and 2020 Pattern Recognition Medal of the International Journal Pattern Recognition. He was a member of NATO Advisory Panel for Information and Communication Security, NATO Science for Peace and Security between 2008 and 2011. Thank you so much, Fabio, for accepting being with us here today and presenting this interesting talk about adversarial machine learning. So the talk is yours, Fabio. You can start.
Thank you, Bassam. And while indeed, I'm really happy to be here today. Thanks for inviting me. Indeed, very, very happy to be here to give this talk, even if only online. I hope, well, in the near future, you can meet in presence. Yeah. Okay.
Thank you.
Anyway,
Thank you.
as you told today, I'm going to speak about adversarial machine learning. That it means that I'm going to speak about the security of adversarial machine learning. To jump into the floor, let me start telling something that probably the most of you are pretty much aware. Today, we are living a very good period for artificial intelligence. Someone speaks about the golden age of artificial intelligence because over the last 10 years, we experienced a tremendous progress of machine learning algorithms, especially for specific problems, specific tasks like image recognition. Maybe you know that for image recognition, that is the task of recognizing one specific kind of object inside one photo. Today, we have image recognition algorithms based on AI, based on machine learning, in particular based on deep network, which provide performances in terms of accuracy better than humans. This has been reported in a clear way for the so-called ImageNet challenge. That is a challenge using a famous and large database of images called ImageNet that is used for benchmarking image recognition algorithm. And during the last edition of this challenge, the performances in terms of recognition accuracy of machine learning algorithm have been better than the performances of human beings, in the sense that the average error of humans for the recognition of the images, of the objects contained in the images of this database, the error is higher than the error exhibited by machine learning algorithm. So, well, we can say that today, really, for some specific task, not in general, but for some specific task, machine learning exhibits superhuman performances in this sense. Given this state of affairs, there is an interesting question boiling behind the scene. That is, this high accuracy of machine learning is also related to high robustness. What I mean, that for sure, for some tasks today, machine learning exhibits very high accuracy, very good accuracy. But one interesting question is, this accuracy is also related to high robustness, in the sense that supposing that you can have some perturbated, some manipulated input data, the accuracy is still high, or maybe we have a problem with robustness for our machine learning algorithm. To answer this question, let me consider a very, let's say, paradigmatic example, in the sense that is really one ad hoc example that I chosen for the purposes of my talk today. And the question is this. Let's consider the two photos, the two pictures that you see on the slide. Of course, at the first sight, you realize immediately that they are school buses, and the two pictures, they look exactly the same. It's really difficult to find any difference. And indeed, believe me, there are really little differences, so little that are not imperceptible to us. So if I ask you, what do you think that about the recognition of these two images by a well-trained machine learning algorithm? Do you think that the recognition should be the same or different for these two images? Of course, the immediate answer is that, one well-trained machine learning algorithm should recognize the two images as belonging to the same object, I mean, a school bus. But around 10 years ago, the machine learning community discovered something that was called an intriguing result. And what has been discovered is that it's possible to find a very small perturbation, let's call epsilon, to a given image, like this image of the school bus, a very small perturbation that you can add to some pixels of the given image. And this perturbation is so small that it's really imperceptible, in the sense that the resulting image that we call one adversarial image or one adversarial example looks exactly the same to us, because we are not able to see any difference. But for many machine learning algorithms, well, the recognition result is totally wrong, in the sense that, as you see on the slide, is recognized as not more a school bus, but one animal, an ostrich in this example. And the interesting thing from the technical viewpoint is that this perturbation that we call adversarial perturbation, epsilon, can be found solving a mathematical problem that is an optimization problem, technically a constrained optimization problem, that we are able to solve using algorithms like gradient descent or variation of gradient descent, which are really well known. And well, to add something, I should say that so far has been proven that this kind of adversarial example, this is the technical term, so this kind of adversarial perturbation, which are able to fool machine learning algorithm, exist basically for all the kinds of machine learning algorithms. Of course, in this example, we are dealing with digital images. That means that we are supposing that we have a digital image and we can perturbate any digital data as we want. So what a related interesting question after this fact that has been published in the literature around 2013, an interesting question that came out in the community is, but this kind of adversarial perturbation, adversarial example, also exists in the physical world. In the physical world means it's also possible to fabricate a real physical object, so that when we show the physical object, for example, to a video camera, we are able to fool, to corrupt the operation of a machine learning algorithm, use it, for example, for image recognition. Also, the answer to this question, I could say, unfortunately, is yes, because some years ago, exactly in 2016, at the top tier security conference, has been reported that there's a quite intriguing result that, well, some researchers reported a result where they was able to fabricate a pair of eyeglasses so that when you wear this kind of eyeglasses and you go in front of a face recognition system, this kind of eyeglasses allows you to impersonate another person, another people. And in particular, the authors of this work, they reported a funny result showing that the gentleman in this photo was able to impersonate the lady in the photo. That is a famous actress, by the way. And the kind of algorithm that you have to use to find how to fabricate this kind of eyeglasses is exactly the same algorithm based on the solution of a constrained optimization problem that was used to find the manipulation to be applied to digital images. And this kind of trick, fabricating adversarial eyeglasses to full face recognition system, is something that really today is not difficult to do and works reasonably well in laboratory condition. I stress the term laboratory condition because it's something that I will discuss more in the end of my talk. In laboratory conditions today, also my students are very good in fabricating this kind of adversarial eyeglasses, and they are able to impersonate other people in front of the face recognition system that we have in our laboratory. By the way, of course, as you can imagine, they have fun impersonating me, of course, because I'm much older than them. And well, this trick and this kind of attack really works well in the sense that fabricating these strange and funny eyeglasses is not so hard in laboratory conditions. Let me tell you something about how these attacks work. How can you fabricate this adversarial example? Which are the fundamental issues behind this? Well, let me start telling that the insecurity, I would say, of machine learning is not something new. Was discovered really a long time ago. I remember, well, more than 20 years ago, that in the spam filtering community, that part of machine learning community working on the development of anti-spam filter, people more than 20 years ago, they already knew very well that anti-spam filters based on machine learning, they are vulnerable, they are not secure. This was due to the fact at that time that the most of anti-spam filters were based on linear models. But it's still true because many commercial anti-spam filters still use linear machine learning model, and linear machine learning models are quite vulnerable. Let me use as an example the case of spam filters. Imagine that you have this email that is a spam email, so it's a bad email that you don't want to receive. And you use a linear machine learning model, so a linear classifier, using a bag of keywords with some related weights, which are positive if the keyword is frequent in spam email, and they are negative if the keyword, the word, is not very frequent in spam email, but is frequent in legal, in normal email. Using a well-trained linear classifier trained on a bag of words, on a vocabulary, is enough to correctly classify that a given email is spam. But unfortunately, it's a long time that we know that for spammers, for people sending spam, it's quite easy to camouflage some words or to add some, they say, good words, which are very frequent in legal emails. And this kind of tricks that in the spam community are called deleting bad words and adding good words are enough to evade many anti-spam filters, especially those one based on linear machine learning models. So while the insecurity of machine learning is something that is not new, but of course, the story is different if you consider non-linear machine learning model. And today, modern machine learning is mainly based on non-linear models. Deep networks are highly non-linear models containing many layers of non-linear transformation. So one interesting question is, what about the robustness of non-linear machine learning model? They are robust, or it's possible to perturbate the input data so that you can force errors to this model? Unfortunately, today we know that also nonlinear models, they are vulnerable. And we discovered this more recently, around 10 years ago, when we tried to attack nonlinear models, finding a perturbation so that we are able to corrupt the operation of nonlinear machine learning model. To explain you how we discovered that, let's imagine that we have a simple machine learning problem. You have a binary pattern recognition, pattern classification problem. You have two classes. Imagine a security problem. So you have two classes, one class of bad pattern, malicious pattern, and one of good patterns, legitimate pattern. Think about the case of malware, for example. You have benign software and malicious software, malware, and you want to recognize the two cases. Imagine that the goal of the attacker is finding a perturbation for a given pattern X so that the pattern is perturbated a little bit, but enough to change the recognition from malicious to legitimate to good. Oh, the interesting thing is that to find this perturbation, the mathematical problem that the attacker has to solve is quite simple. Is this minimization problem with a constraint that you see on the slide? What the attacker has to do to find X apex, the perturbated pattern, is to minimize the value of the function g of x so that the value becomes negative, because negative values are for good patterns, for legitimate pattern. Also taking into account a constraint, because in any real application, the attacker doesn't want to perturbate the input data too much, because while large perturbation often are not allowed. So there is a maximum, Dmax perturbation that is permitted. But the interesting thing is that while this mathematical problem that the attacker should solve to find one adversarial example, I mean to find a perturbation that allows to evade, to fool this simple binary classifier, can be solved using gradient descent, in particular a version of gradient descent algorithm that is called projected gradient descent. Because suppose that the function g of x is differentiable, the attacker can find the minimum of the function subject to the constant and find a perturbation that is enough to evade your machine learning model. And well, the gradients of the function is analytically doable in many cases. When the attacker, when your machine learning model is not differentiable, the attacker can use another trick that I show you soon. Well, this kind of attack can be really implemented using 10 lines of codes in any language that you like. We did that, me and some colleagues, around 10 years ago, and we wrote really 10 lines of code based, the mathematical algorithm is basically the gradient descent, and we was able for the first time to show that nonlinear classifiers are vulnerable. That to give you an example, a very simple example, 10 years ago, we reported result, for example, also for simple case, showing that if you imagine that you have, for example, a nonlinear support vector machine, solving a very simple problem, recognizing 2 digits, 3 and 7, using gray level images, I can take this picture representing the digit 3, and if apply to this image the algorithm that I have shown you before, this one, I can find an adversarial example. So one version of the initial image manipulated really just a little, because you see there are really few modifications, but this digit on the right, that is still 3 for us, is recognized as 7 by the nonlinear support vector machine. This is what in the literature are called white box attacks against machine learning. White box because we are supposing that the attacker knows all the details of the machine learning algorithm. Of course, this is true, for example, if the machine learning algorithm is open source, is available open source. But what about attacking a machine learning algorithm if the machine learning model is a black box, in the sense that you don't know everything, you know something maybe, but not everything, or in the worst case for the attacker knows nothing? Well, over the last 5 years, many research works shown that it's still possible to use a simple trick also to attack machine learning algorithm when the attacker has a partial knowledge. For example, when the attacker doesn't know the training data that you used for training your machine learning algorithm, suppose that the attacker anyway have some training data similar, so the attacker knows well the problem that your machine learning model is solving. What the attacker can do is sending queries to your machine learning model, getting the recognition result from your machine learning model. That is something that usually is possible for the attacker, supposing that you are interested to provide your model as a service, for example. So you provide replies for queries. And so the attacker is able to learn a sort of copy, an approximate version of your machine learning model, and then try to attack the copy. And if the attack is successful, use the same attack against your model, even if the attacker doesn't have a clear knowledge, a perfect knowledge of your machine learning system. This is basically the underlying idea that can be also used to attack any model that you don't know exactly. And is what is called the transferability of attacks in adversarial machine learning. And mostly this strategy can be also used when your model, the model that you want to attack is not differentiable, because you can try to create a model that is differentiable, so you can use gradient descent to create adversarial example. So, well, the take-home message here is that, well, it's a longer time that this stuff, this research stuff is explored in many ways. So, well, today we know that there are really a huge number of papers published, probably around, well, my count is that we have around 10,000 papers already published on adversarial machine learning. And on the basis of this knowledge, I can say that we have strong evidences that linear and nonlinear models, machine learning models, are highly vulnerable to this kind of evasion attack, at least in vitro. I put in red this sentence because I will discuss this argument more in the end. In vitro means in laboratory condition. This is an important fact. Keep in mind, because I will discuss this again in my conclusion. And given this state of affair, what is very important, so the take-home message is that today, when you evaluate the performances of your machine learning model for any security application, assessing the accuracy of your model is not enough. You should also assess the robustness using the concept that I call security evaluation curve. So you should try to assess how the performances of your model, they decrease under attack. Under attack means when someone is going to perturbate, to manipulate your data under increasing value of the perturbation. Let me tell you something more about this concept of security evaluation curve to make it clear. Let's suppose that you have two machine learning models, classifier A and classifier B, and here on the x-axis, you have the perturbation, different levels of perturbation that the attacker can add to your data. When you have zero perturbation, can happen that classifier B, the green classifier, the green line, is better because it's more accurate. But very often in real application, you can realize that under attack, under perturbation of the input data, while the other classifier that initially with no attacks is better, is more robust, and the other one is less robust. So evaluating the robustness under perturbation of the data is something that is mandatory to assess what is the best classifier, the best machine learning model for security applications. To do that, let me recommend, of course, well, I have a conflict of interest, but let me recommend to have a look of the open source Python library that we developed in my laboratory. It's an open source Python library that you can use for evaluating the security of your machine learning model. So for computing exactly that curve that I call it, the security evaluation curve. So you can check how much your machine learning model is robust against increasing level of perturbation of the data. So you can discover, coming back to this slide, when, well, if the maximum perturbation, well, still provides a reasonable accuracy. And for any task, for any practical task, you usually can get or have an idea about what is the maximum perturbation that the attacker can add to the input data. Well, of course, one interesting question that has been debated a lot over the last 10 years is why machine learning is so vulnerable. Why is enough, in some cases, a small perturbation and the recognition result is totally wrong? There are many answers that has been given to this key question. Well, someone say, well, the problem is that machine learning is based on a very strict assumption, the so-called high ID assumption, the assumption that data have been identically independent distributed. That means that future data should be quite similar to the training data. I mean, should come from the same distribution. And unfortunately, in security application, in adversarial machine learning, this assumption is not true. Well, this answer is okay, but today I want to tell you another answer to this question that I like more, and is related to the magnitude of the gradient of machine learning algorithms. The problem with many modern machine learning algorithms is that the function g of x that you learn with machine learning has a large gradient, a large derivative. And when a function has a large derivative, of course, you have a large sensitivity. Sensitivity means that small changes of the input data, are enough to change a lot the value of the function. So you have what mathematicians, they call sensitivity. Sensitivity means that small changes of the input they cause large changes of the output. Why machine learning in general exhibit large gradient, learn a function with large gradient? The answer is very simple, because large gradient is very useful during learning, is very useful during training, because large gradient means that learning is fast. But unfortunately, large gradient is good for learning, but after learning at test time, large gradient means that your machine learning model is very sensitive, and this should kept in mind. Let me tell you something about the defenses. Of course, this is a security problem. And for any security problem, you have the attackers, and so you have someone who try to defend. So what about the defenses against this kind of attack? I don't have enough time to go into the details, but I want to tell you something about the two main categories of defenses. Today, at the state of the art, there are two main types of defenses against adversarial example, against perturbation of data. One is based on robust optimization. I will tell you something more in the next slide. That is using the mathematical framework of robust statistics to develop machine learning algorithms which are more robust against perturbation. This is what is used in adversarial training and some type of regularization. And the other is developing technique to detect adversarial example and to reject. So to avoid that your machine learning algorithm make any decision for adversarial example, which are too much perturbated. Let me tell you something more about the two defenses, just 2 slides more. What is robust learning, robust optimization? Well, in technical terms, is simply that, the mathematical framework of learning is based on minimization. You minimize a given loss function with respect to a distribution of data, with respect to your training set. Robust learning is a different problem. You minimize your loss function, but also take into account the maximum perturbation that a given attacker could apply to the data. So you change the mathematical setting from a minimization problem to a minimization maximization problem. That, of course, unfortunately, is more complicated from the mathematical viewpoint, because you have to solve a min-max problem, not only a min problem. But when you are able to solve this problem, you have the advantage that, for example, consider the case on the right. Well, if you have these data, green and red points, you can imagine that, well, the dotted line is a good model, linear model. But if you take into account the perturbation, so if you also take into account the maximum perturbation that you can have, you could discover that the robust version of your model that is robust against perturbation is not the dotted line, but is the solid one. Unfortunately, solving a min-max problem is very hard, is a result that is very well known from game theory. You can solve it in some particular cases, for instance, when you have a linear loss function, when you have a linear classifier. In this case, the min-max problem can be transformed in a minimization problem plus a regularization term. In the general case, you can solve min-max, but it's very computationally expensive. What about detecting and rejecting adversarial example? This is a defense that works well when adversarial example, they are reasonably far from the distribution of the legitimate data. In this case, you can try to use machine learning models which have closed boundary, and we can try to detect and reject adversarial example. Honestly, after more than 20 years of work in this field, what I can say you is that detecting and rejecting adversarial example work reasonably well when adversarial example are quite similar to outliers. In other case, it works, but you can have a high rate of false alarms, let's say. Just one slide to tell you that today, for the sake of time, I focused on what is called evasion attacks in adversarial machine learning. But there are other types of attacks against machine learning. Well, not only evasion, but also attack which can affect the training phase of machine learning, called poisoning of machine learning, and also other attacks which try to do reverse engineering of your machine learning model, or to steal private confidential information contained inside your training data. But well, for the sake of brevity, if you are interested to a more comprehensive overview of different attacks, I refer to an overview that I published a few years ago. So let me go to conclude, speaking about one issue that I do think after a long time that I do research in this area is really important today, and is related to this question: does AI security really matters? What I mean, well, so far we published tons of papers about AI security, adversarial machine learning. But now it's becoming really interesting, especially from the cybersecurity viewpoint, the question, this kind of attacks really exist in real setting in the wild. What does it mean? Because today, really, companies, institutions, governments are pretty much aware that the security of machine learning is very important. If you have a look of reports about the strategies for artificial intelligence of different countries over the world, you find that all the institutions of the governments and also big companies are really aware and quite worried about the problem of AI security. So this is considered today really an important topic. And I do believe that it is an important topic. But what I want to discuss, what I want to share with you now is this problem. Even if today we know that the problem exists and is quite serious, what is lacking is that we are not very sure about how many times this kind of attacks really happens, really exists in the reality. Because the evidence of attacks against real AI system in real operational condition is a little bit unclear. Yeah? Even if, while you can read many papers telling, well, this is a very serious and problem, is a clear and present danger, while the situation is not exactly this, the problem exists, is important, but we have to understand much better under which condition it really exists in the wild, in real settings. And this is related to the distinction that I call the distinction between in vitro versus in vitro research. That is a concept that is very well known in medicine, in biology. Medical doctors, they do a strong distinction between the results that they get in vitro, I mean in laboratory condition, with respect to the result that they can obtain in vivo, especially when they want to use drugs for humans. Because after a lot, really tons of paper of machine learning security, today, as I said we have clear evidences that any model can be attacked in laboratory. There is no way to protect. And unfortunately, in laboratory condition, we know that strong attacks are very hard to prevent. But honestly, we should say to the community and to the stakeholders, to the institution, that all the research that we have done so far in laboratory condition dealt with particular settings, considering imperceptible perturbation, considering white box attacks. That means that we assume that the attackers know more or less all the details of the machine learning algorithm, that the attacker can send an unlimited number of queries. and only a small fraction of the research paper dealt with more realistic settings. And unfortunately, realistic settings are quite different. Yeah, you have to consider black box machine learning with very limited possibility to send queries. In many commercial machine learning systems provided as a service on the cloud, while you have a limited budget of query, yeah, that you can send, and attacks need not to be imperceptible. So there is a strong difference between research in vitro for the security of for evaluating the security of machine learning, and what you can do in vivo, in real condition. So what I want honestly to share with you, to say you, according to my experience, is that today we don't know if and when reported attacks in academic paper are really feasible and really work against real AI system in real setting. Well, this can appear a bad news, but it's not bad news. Why? Because we don't know, and so maybe we could discover that in real setting for real system, the problem of security exists, but is less dramatic, is less serious that we have discovered, that we have experienced it in laboratory conditions. So there is hope in some sense. And maybe while our results as a research community maybe are a little bit too pessimistic, maybe because honestly, we don't know, because there is a lack of result in real condition. And so we don't know when we really need defenses. Maybe we could discover, I hope in some years, that for real machine learning systems, under some settings, we don't need defenses, because attacks that we have developed in laboratory are not feasible in the reality. And we could discover how to develop practical defenses, something that is still lacking today. This brings me to the last slide and my conclusion. I want to share with you what I call my dream project for the next 3 years. Dream because, well, suppose that well, I'm good enough that I get enough research funds. What I want to do in the next 3 years is to develop what I call a cyber range for AI security. Maybe you are familiar with the concept of cyber range. It's something that it became very popular in cybersecurity over the last 5-6 years. A cyber range in cybersecurity is a virtual environment simulating in a good way a real IT infrastructure containing networks, containing computers, containing servers, and also containing the devices that you use to protect your IT infrastructure. So using a cyber range in cybersecurity, you can really simulate real attack or realistic attack, and to evaluate how much your defenses are good. And you can have teams of people that you call red and blue teams, which are defenders and attackers. I do believe that to make a big progress in the evaluation of the security of machine learning, we have to develop, well, the same thing for AI security. So developing cyber ranges for AI security, so a virtual environment where we are able to simulate more realistic installation of machine learning system in real conditions. And so we are able to evaluate in a more realistic setting when the attacks that we developed in laboratory are really feasible for real infrastructure, for real setting. And when the defenses are really necessary, and when our defenses are effective in real setting. And mostly we can imagine that also for machine learning, inside a cyber range, we can have teams of red and blue people, which are attacker and defenders, people who attack machine learning systems inside a cyber range, and people whose goal is defending machine learning system. So I do believe that this can be beneficial for the progress of AI security. That's all. Thank you for listening, and thank you again for inviting me.
Thank you so much, Fabio. Thank you so much for this interesting talk. So we do have some questions from the audience.
Yes, please.
So yeah, the first question is, do you think that optimizing models to fit them on embedded targets, quantization layer fusion, will make models more vulnerable, for example, to evasion attacks?
Okay, I see.
Yeah.
Well, yeah. Well, I try to give you a frank, a genuine reply. I don't have any first-hand experience, but I do believe that if you optimize a model to fit on embedded target, well, in principle, it's not clear if you can make the security worse or better. Because, well, for example, if you imagine that if you use an embedded device and maybe you have, let's say, to reduce the quantization of the information that you can store on the device, this could be maybe beneficial. So, well, to be honest, the most frank answer is that, well, it's something that should be investigated. Yeah, it's, okay. I don't see any clear reason to say that it's better or worse.
Okay, so he was asking some context. Are you aware of any delivery method for this type of attack, like sensor hijacking, EMF injection? For
there are some examples. For example, there is a very recent result showing that it's possible to, well, create adversarial example against, Amazon Alexa or other home assistant which are able to recognize your voice. Yeah, so there are some. So it's possible to create adversarial example to fool the speech recognition system of the, let's say, home assistants that we use, like Amazon Alexas or other.
Okay. Another question, could power analysis of the model help guide the black box attacks into getting to more or less a gray box type of attack?
Well, power analysis, maybe yes. Well, if power analysis, I guess that you mean one analysis in the frequencies domain. I mean that this is the point, in the frequencies domain. Well, I don't know any work exactly that try to do that, but there is a lot of work that try to analyze, let's say, how the information changes during the propagation inside a deep network, layer after layer. And there are some techniques that have been proposed that, well, if you are able to analyze how the information is propagated from the input layer to the output layer of one deep networks, you are able to distinguish the propagation of normal data from the propagation of adversarial example, because there is a different mechanism of propagation. Okay. But unfortunately, all the work that I know, well, it works, but it produces a lot of false alarms. So, well, I don't know if, well, there are also some application of chaos theory, yeah, to analyze the weights of deep neural networks. Yes, they work, but in laboratory conditions.
Okay, I see. So there is another question. So he said, okay, good day, Prof. I'm working on virtual machine learning in the physical world. Do you believe that it makes sense to pursue physical adversarial examples that can work practically in an uncontrolled physical environment, which may impact the learned adversarial perturbation in different ways? Specifically speaking, with respect to generalized object detection problem, where the modern detectors are highly robust to random perturbations and occlusions in general.
Yeah, well, okay. In laboratory conditions, so again, at the state of the art of research, has been proven that yes, it's possible to create, let's say, adversarial physical object. You remember the example that I have shown at the beginning, the adversarial eyeglasses. so that, well, you have a good chance to evade in the physical world a machine learning algorithm. Of course, well, is another story if you are, what is the probability of success of this kind of attack in a real and very complex setting? I mean, yeah, well, that is something that, as I said, in the end, is not clear enough. Anyway, yeah, I don't agree totally with the part of your question telling that object recognition systems are really very robust to, let's say, different condition of the inputs. Yeah, they are very robust to all the variation, all the changes, which are very well represented in the training data. But well, it's very well known that even if you don't have any adversarial example, but you simply have what is called one out of distribution data, that means some data outside the distribution of the training set, well, the robustness of machine learning for object recognition is not so high. So it's a general problem. It's a general problem.
Good. So, okay, there is another question, Fabio. So the question is, does the machine learning model trained in an unsupervised way, examples such as for self-supervised learning, are they vulnerable to adversarial attacks too?
Yes, well, definitely yes. I did a lot of work on that. Unsupervised machine learning, I mean, for example, clustering algorithms, they are vulnerable. They are vulnerable to what is called not evasion, not the attack that I have shown you today, but another kind of attacks which are called poisoning attack. That means that if you are if the attacker can inject a small percentage of manipulating data into, let's say, the data, the clustering algorithm can be, the clustering result can be changed a lot. So yes, and the percentage of data manipulated should not be so high. So the answer is yes. This kind of problem of sensitivity also happens for unsupervised machine learning, and for sure for semi-supervised.
Okay. Okay, I have myself a question, Fabio.
Yes, please.
I mean, regarding, let's say, the pervasive machine learning, when we collect continuously the data, I mean, how efficient, I mean, such adversarial attacks will be against such, let's say, continuously collected data?
Yeah, well, you know, unfortunately, the continuous collection of data, from one end, could be an advantage for the security if you imagine that well, when people they discover new adversarial example, they provide you this example for retraining. So from one side could be beneficial, but for the other, on another side is a serious problem, is a serious danger, because you know, many machine learning algorithms today are trained using the few large data set that we have. So imagine what could happen if someone is able to manipulate the large benchmark data set that really many peoples and really many companies are using. So while the continuous collection of data is from one side beneficial, but the other side, the practical problem is that we should be able, we should become able to certify the quality of the training data that we are using, especially when we use this data for commercial products, because otherwise we can have a problem. There is a kind of attack that has been discovered recently that is called backdoor. That is the same attack well known in computer security. That means that it's possible if you can inject some spatial example, training example in a training set, you can create a so-called backdoor in a machine learning system, exactly as we know very well in classical computer security. So there is a debate, and there's a very interesting problem.
Good, thank you so much, Fabio. Thank you so much for this interesting talk, for your, let's say, interesting responses also for the different questions. And yeah, that's it. I would like to thank you. I'd like also to thank the audience for such interesting questions. And we will get in touch with you soon, Fabio. Okay.
Thank you. Thank you very much. And thanks again
so
for
much.
inviting me. Bye-bye. Have a good day.
Thank you. Bye-bye. Have a good day.
Bye.
Bye.
Bye-bye.